Welcome to our second session on survival analysis. Today we're going to introduce proportional hazards, and you'll learn to perform and interpret the Cox proportional hazards regression and be able to define time-dependent covariates and what they're used for. You'll also learn the differences between parametric and semi-parametric survival models and identify the types of situations where a parametric survival model might be useful. So we'll start with a review of the survival and hazard functions that we introduced last time, and then go into the Cox proportional hazards model, how to interpret it and perform inference with it, along with what this proportional hazards mean and what to do when hazards are not proportional. And then we'll end with parametric versus semi-parametric survival models. And this is mostly from your textbook in Chapter 6. There's a bit of extra material that I'll cite in the slides as well. So let's start with a bit of review. Recall this acute lymphoblastic leukemia data set that was a study of this treatment 6MP against a control group with the outcome of the time to remission for these patients. So there were 42 patients that had achieved remission from their induction or their introductory therapy, and then were randomized in equal numbers to this treatment or a placebo group. And then the time of the survival time in this case was from the randomization, where they were assigned to the treatment or placebo group, until relapse. We went through a calculation of the survival function. This is a survival table here, starting with, and this is just for the placebo patients here, showing the start of the 21 patients, and then at each time period where there was either a relapse or a censoring event, we calculated this survival function and showed how the survival probability is just a product of the probability of surviving up until the previous time times the conditional probability of surviving at the next time, conditional on having survived to the previous time. And that way you get this always decreasing survival function that starts at 100% at the start of the study and goes to the final estimated probability of survival or non-relapse at the end of the study. And this is the Kaplan-Meier estimate of the survival function. Although we did it in the lab by hand, it's quite a bit easier to do this with the survival package. And this is a Kaplan-Meier plot that shows this estimated survival function for these two groups. So you can see here, this is that what we call the risk set, the number of risk at each of these times. And you see the survival starting at 100%, dropping quite quickly for the placebo group down to 0% survival at just over 20 weeks, at about 24 weeks or something here. Whereas in the treatment group here, you see a higher survival probability and ending at about 50% towards the end of the study. So the survival function has an intuitive interpretation. It's the probability of being event-free at time t, or equivalently the probability that the time of survival is greater than this time t. And then the cumulative event function is just the reverse or the complement of the survival function, 1 minus the survival function. So it's the probability that the event has occurred. So if survival is referring to non-relapse, then the event function is referring to relapse. And then finally, the hazard function, which is what we refer to when we'll talk about proportional hazards, is this short-term event rate. So it's a derivative of this cumulative event function. It's the probability of an event at each moment in time, given that you have survived until that time. So if this is what a survival function looks like, I'm showing here what the corresponding hazard function looks like. And the hazard function for this control group is a little bit it's a little bit funny as we get up to here, just because there are so few patients left in the placebo group at this point that we don't get a good estimate of the hazard function. We have a better estimate of it down here, but approximately what you expect, what proportional hazards mean, is that these two lines are parallel to each other. So here we see an increasing hazard with time for the treatment group, and you see an approximately equivalent increasing hazard up here. It's a little bit hard to tell for this data set because it's so small and there's such a high rate of attrition in the control group. But we can introduce the hazard ratio. So if we're comparing two groups, such as here a control and a treatment group, the hazard ratio in general could be a function of time. If we had two completely different hazard functions for these two groups, so I'm showing them both here as a function of time, then the hazard ratio would also be a function of time. So it changes, this ratio changes with time. So in this case, the interpretation would be the risk of event for the treatment group compared to the control group as a function of time. Now, under the proportional hazards assumption, the definition is that this hazard ratio does not vary with time. So that hazard ratio as a function of time is just a constant hazard ratio. It does not vary with time. At all times, it is just this HR. So that is an assumption, and as with all the assumptions that we've done, or I don't know if all, most of them, this is an assumption about the population. So in a sample like we saw in the previous slide, there can be variation, sampling variation, especially for small samples. But the assumption is that if we had a large enough sample, this hazard ratio would actually be constant. In the Wittinghoff dataset, they have another example here of a very nice proportional hazards dataset. And you can see here, we're looking, let's see, this is the estimated hazard per 100,000. And you see that it starts high and decreases. But it looks like a pretty constant multiplicative factor. If you were to take any one of these as the baseline hazard, you could multiply it by a constant to get one of these other hazard curves, and a different constant to get the third hazard curve. So the hazard function itself does not have to be constant. You can see it's a function of time, but the ratio between these curves has to be a constant over time. That's what the proportional hazards assumption means. All right, going back again to our leukemia data set here, yet again is our Kaplan-Meier estimate of the survival probability. I want to demonstrate for you one more plot. This is called the log minus log plot, and this actually is the recommended way of assessing the proportional hazards assumption, because on this scale, it's a little bit less sensitive to fluctuations than that hazard plot that I showed you. But in a proportional hazards data set, these two lines will be parallel. In many cases, you will see a straight line, but the important thing is that these lines are parallel. So this makes me think that the proportional hazards assumption is a pretty good one for this data set. All right, it's been a little while since we introduced a new regression model, so let's review again the previous regression models that we have developed from the generalized linear model. So the systematic part of the generalized linear model has always looked like this. The expected value of the outcome conditional on the predictors is equal to this, this linear combination of the predictors multiplied by their coefficients. And for logistic regression, we used the logit link function with the outcome being a binomial probability. So the probability of the one outcome against the reference outcome, with the logit function being the log odds. But on the right side, it was just the linear predictor again. Then for the log linear regression, that is for the count models, we had a log link function and then the linear predictor on the right. And then the other difference between these was the count models, in that for logistic regression, our error model on the outcome was the binomial distribution, and in log linear regressions we used the Poisson distribution and we used the negative binomial distribution for the random distribution of outcomes for any given combination of the predictors. That is the conditional distribution of the outcome variable. So what will this look like now for the Cox proportional hazards model? So this model we use it to assess the relationship between a right-censored time to event outcome and predictors, where the predictors can be categorical variables such as treatment groups, as we just used in an example, or continuous variables. And in this model, it's actually not going to be an expected value of y given x, but what we're modeling is actually the log of the hazard ratio. And this hazard ratio, as we saw under the proportional hazards assumption, does not depend on t, but it does depend on these predictors xi. In general, it does depend on the predictors. So the hazard ratio, as we showed, was equal to the hazard function as a function of time and the predictors. So, and then on the denominator, this is what we call the baseline hazard. And the baseline hazard, it's like the reference group. In linear regression and logistic regression and all of the regression models we've done, there's always been a baseline group. And that is the same here, except that the difference is, instead of, say, in logistic regression, where the baseline group would have had a certain probability of the outcome, and then the probability of that outcome for the other groups would be the baseline probability, or say the baseline odds times the odds ratio for each of the non-reference variables that we had. So it's similar here, except that the ratio is of these two hazards. So it turns out that the application of it looks very similar to maybe the log linear models are the best, because or the best direct comparison, because we have this log function, but that's the only relationship or the only transformation between this linear predictor and this hazard ratio. So I have a question for you. Is this a multiplicative or an additive model? Well, it's a multiplicative model, because if we add something to this linear predictor, so say x1 is a binary variable, in the non-reference category we add beta 1, that adds something to the logarithm, so it multiplies the hazard ratio. Another way to look at this formula would be that the hazard ratio is equal to the exponent of the linear predictor. Or for each of these coefficients, as we'll see in the model, you would have to exponentiate it to find the ratio that it contributes to the hazard ratio relative to the reference group. So to summarize interpretation of the coefficients, again, it is similar to other multiplicative models that we've covered, but for a categorical or binary predictor, beta is the logarithm of the ratio of hazards of the comparison group relative to the reference group. For a continuous predictor, it's the log of the ratio of hazards for someone with a 1 unit higher value of that continuous predictor, such as 1 year older if you had used age or time as a continuous predictor, which we don't usually do, but something else like 1 millimeter of mercury in blood pressure, etc. So if that coefficient is close to 0, that means that the hazard ratio e to 0 is close to 1, then that predictor does not affect survival. If the coefficient is negative, so the hazard ratio is between 0 and 1, then that predictor is protective. It means there's a reduction in hazard and an improved survival. And finally, if the coefficient is positive, then the hazard ratio is greater than 1, and that predictor is associated with increased risk or decreased survival. Once again, you can use the Wald test or the likelihood ratio test for coefficients to test the null hypothesis that a coefficient is equal to 0 and against the alternative hypothesis that it is not equal to 0, which is equivalent to the hazard ratio being 1 or not equal to 1. And then these confidence intervals are typically obtained from the Wald test and shown in the output of your regression table as you're accustomed to for the other regressions. So again, a lot of this looks pretty familiar. We have here the alternative category is 6MP. We have a coefficient of negative 1.57. What does that mean? Again, it's negative. That means that the odds ratio is less than 1, and that means that this is a protective variable. As we saw, the treatment seems to be effective, and there is an improved chance of non-relapse in this treatment group. So yes, actually this is the odds ratio. It also shows us the exponent of the coefficient. So it shows us that the hazard ratio is 0.2, meaning that the hazard is only about 1/5 in this in the treatment group compared to the baseline reference or placebo group. Standard error is quite small. P-value is very small here, so we would reject the null hypothesis. And this is just showing it again for repeating the hazard ratio, giving the inverse hazard ratio. This is just 1 over 0.2076, so you can see it's almost 5 times lower hazard along with confidence intervals. And then again, we have some extra information down here. The most interesting thing for you probably is this log rank test and likelihood ratio test. And this is on the full model. So whereas you'll see here results for each variable from the Wald test, this will be this is for the full model compared to an intercept-only model, showing that the predictors are predictive of survival. So before we get into parametric survival models, I'm going to tell you that the Cox proportional hazards model is a semi-parametric model. What does that mean? I mean, it could mean a bunch of different things, but what I mean by it here is that it does make some assumptions. It assumes proportional hazards between the different groups. So that's a parameter, this proportional hazards. But there's no assumption on that baseline hazard. That can take any form at all. The only thing you recall from the first session, we saw that what really mattered was the order in which events or censoring happen. So the very last one, it doesn't matter if it happens at 50 weeks or 500 weeks, it's only the order, and there's no assumption on the actual shape of this, this H0, the baseline hazard. So it is a robust approach if this proportional hazards assumption is not violated. If it is violated, then time-dependent covariates can be a solution for resolving apparent violations, and we'll talk about that a bit. So in summary, the proportional hazards assumption means a constant hazard ratio between groups over time. And that corresponds to a linear association between the natural log of the relative hazard and the predictors, and a multiplicative relationship between the predictors and the hazard, which is the basis for the inference that we did on the previous couple of slides. And just as a note, we also are assuming uninformative censoring. That's not so easy to deal with if that assumption is violated. Okay, so what do you do if the proportional hazards doesn't hold? Remember, we did that log-log plot. We saw a nice parallel line between them. We also, when we made the Kaplan-Meier plots, we saw these kind of, gradually widening survival lines. What if it doesn't look like that? What if the log-log plot shows like crossing over lines? You can even see that sometimes on the survival plot. Actually see two survival curves where one group is doing better for a while and then they're getting worse. Well, time-dependent covariates is an option, and all it is a predictor whose values may vary with time. You can define these how you want. You can define like, a step function that changes in time, a totally arbitrary thing. It can be defined, say, as the dose of a treatment that is given over time, so just the dose in each section of time. But there's a very, very important rule in doing this, and that is you cannot look into the future in your analysis, even though your analysis has taken place in the past. So it's surprisingly easy to break this rule. It sounds simple, but because you have all of the information when you're analyzing the data, it can be a little bit difficult to put yourself back in the beginning of the study and think about what information you have at each point. So if you're going back and thinking about your analysis, you have to think about predicting the hazard and events of each person at that point in time without using information from the future about what eventually happens to that patient. That's cheating, right? It seems obvious, but it's actually an easy mistake to make, and one that there are plenty of examples of this mistake in the literature. And it can cause some severe bias if you don't follow that rule. Some examples, and this is a hyperlink here to where I got these examples from. One they had was breast cancer chemotherapy patients divided into groups based on how much of the planned dose they received. So that's looking into the future because they were divided into groups at the beginning of the study when you don't know how much of the planned dose they eventually received. So if one patient received their full dose and another one only received half of it before they were taken off, you don't know that at the outset of the study, so you can't use it to split patients into groups. You can only use things that you know at the beginning of the study, right? And that turns out to cause severe bias in your estimate. It makes it look like, so if you have patients who did not receive their full dose because they died, it makes it look like not receiving your dose is very bad for survival because those patients died. But it's looking into the future, it's cheating. Another example is patients divided into groups based on early response to treatment, such as the shrinkage of a tumor, lowering of cholesterol, etc. So again, you're splitting patients into groups at the beginning based on something that happens in the future, and you cannot do it because even if there is no relationship between the lowering of cholesterol or the shrinking of the tumor and your outcome, the fact that that you use this information from the future to split your groups, it takes that information and puts it and puts it at a point of time when you don't have it. A third one is the interpolation of the values of a laboratory test linearly between observation times. So it seems honest enough. It's like you have blood pressure readings at each at two different times, and you assume that it moved linearly in between those times. Well, during that time in between, you're using a measurement from the future to say what it is in between. And you don't have that. All you know is what it was at the previous point, so that's not allowed. Removing subjects who did not finish the treatment plan. So that would mean taking the subjects who did not make it all the way through treatment for some reason or another, going back to the beginning of the study and removing them. Again, you're using information from the future to remove them now. There are all kinds of potential problems with that, such as if they didn't finish the treatment plan because they were at worse health, or just the fact that they finished the treatment plan means that they're guaranteed to have survived that long. That's called a mortal time bias, which I'll define in a later slide. And another one that sounds innocent enough, imputing the date of an adverse event is midway between observation times. Again, it's taking time at that midway point and borrowing information from the future. So there's a nice page about using PDF about using time-dependent covariates and time-dependent coefficients in the Cox model. It's one of the help vignettes for the survival package. So mortal time bias is one example of this looking into the future. And here is a published example of a report that new statin users had a 26% reduction in the well, I shouldn't say risk, it's hazard of diabetes progression with 1 year or more of treatment relative to never users of statin. And in this study, new users excluded those who had received a lipid-lowering drug from 3 years before to 6 months after cohort entry. So this was surprising because a hazard ratio of greater than 1 was expected, because people whose diabetes progresses are more likely to develop cardiovascular disease, an indication for statins. So more as a result of confounding, but still in this observational study, this hazard ratio was in the opposite direction than had been observed in other studies. But it was the result of an analysis error. So why is that? What was the analysis error? Well, the basic error was this looking into the future, that the new statin user group was defined based on future initiation of statin usage, and that is knowledge that was unknown at the time of entry into the study, and this was used as a covariate or a predictor of outcome based on information from the future. So in practice, in this case, what that meant was that there were guaranteed to be no events for statin users from cohort entry to the initiation of statin use, and thus all persons in that treated group were immortal from time 0 until they started statin treatment. They could not progress to diabetes, and so that period of immortality made the treatment look more effective, and that is an example of immortal time bias. All right, finally, I'm going to give a brief introduction to parametric survival models. So parametric models are those that estimate additional parameters for the baseline hazard. So rather than the semi-parametric model that we had before that assumed no particular form for the baseline hazard and only that all hazard functions were proportional to each other over time, this actually models the form of the baseline hazard. So two of the most common ones are the Weibull model, where the hazard function is some polynomial, and the exponential model, where the hazard function is a constant over time and the survival function is exponential. And since a constant is a special subset of polynomials, that is just a special case of the Weibull model. An example of where you see a constant hazard over time is a healthy population with randomly occurring events. So that is a constant hazard over time. These are just two examples. There are many other options for assumptions to be made on the distribution of baseline hazards. The most common implementation involves a log transform of the time variable, and in this case these can be interpreted as accelerated failure time models. That is a factor of 2 in here. It's no longer a hazard ratio, it's a survival ratio. A factor of 2 would mean that you double the time to event compared to the baseline. So the interpretation of the beta coefficients is different than the Cox model, where the beta coefficients are the logarithm of the hazard ratio. In accelerated failure time models, it's the log of the survival time ratio. Sorry, I missed the spaces in there. But it's, if you take the ratio of survival times, say that the treatment group is expected to survive twice as long as the reference group, then the coefficients are the logarithm of that ratio. And because this is related to survival times instead of hazards, the sign is opposite. That is, if your hazard ratio is positive, then the AFT sign is negative. They're opposite of each other. Why would you use one of these models? Well, they can be more powerful if the assumptions are correct. So if you have reason to believe that this model for the baseline hazard based on previous data is correct, then in general, when you make correct assumptions, you get a more powerful model. So better ability to detect differences, and that might be especially helpful with small studies and small numbers of events. It also has some extra capabilities. You remember those survival functions that we estimated with Kaplan-Meier? They're very jagged. They're based on just the data themselves, whereas with these you get a smooth estimation of the baseline hazard and the survival function. You can perform extrapolation, which is generally risky, but it's possible with these models because you have an actual functional form for the model, and they can also handle more complicated censoring. So whereas the Cox proportional hazards model is appropriate for right censored data, you can handle all kinds of censoring with parametric survival models. So there are some cases where you just need to use a parametric survival model, either because of the censoring that's present, because you have to do an extrapolation, you need a smooth estimation of the baseline hazard, or you need a more powerful model and you have good reason to expect that you know what the form of the baseline hazard is. They're easy to interpret in that the coefficients are log of survival time ratios. In that way, they're easier to interpret than a hazard ratio. This is a much more intuitive entity. And they're also easy to fit. All you have to do is replace Cox pH from the survival package with SurvReg from the survival package. Their drawbacks are, one, that they depend on correct specification of the baseline hazard model. So just like with all parametric models, if your model is wrong, you can get misleading results from them. Also, even if they are correctly specified, they may not provide much improvement in efficiency or power, especially for larger sample sizes, but generally the Cox proportional hazards model is a reasonably powerful test, even though it's only semi-parametric. And then finally, it still does make a proportionality assumption, but on the survival functions instead of on the hazard ratio. Thank you for your time, and we'll go now to the lab.